Good morning, students. In the last lecture, we did the basics of the atomic structure. In today's lecture, we will start with the your first chapter, that is on crystallography. Okay, if we look into the general form of the states of any matter. So we have three different states in which a matter can exist. Those states can be either in the gaseous state, or in the liquid state, or in the solid state. Okay. In the gaseous state, the atoms of the element, they are in total disordered shape. There is no order in which the atoms they lie. They are moving randomly, and there are a lot of empty spaces that are there, and the particles, they have complete freedom of motion, and they are placed far apart from each other. Okay. Now, if we start cooling this gas, and at a certain time, at certain stage, the gas will turn into the liquid state. Okay. In the liquid state, the particles or clusters, they are again free to move relative to each other, and but the particles, they are much closer to each other. Still, the order is not in a definite shape. Again, the particles, they are in the disordered manner. Okay. Now again, if I again start cooling the liquid, at after certain state, the liquid starts to convert into solid form. Now here you can see that there are two types of solid forms that are there. The first is the crystalline solid form. In the crystalline solid form, the atoms, they are placed in a well arranged ordered manner, and they are placed very close to each other. Okay, so the arrangement of atoms is in ordered form. Okay. Now this crystalline solid is formed if the cooling rate from liquid to solid is maintained at a certain predefined rate. Okay. Now if the cooling is done abruptly or very fast, the time required to arrange the atoms in the ordered manner is not there, and the cooling takes place rapidly. So the arrangement is not in the ordered manner, and the solid formed is you can see this diagram here. The arrangement of solid the atoms is not in the ordered form, but it is disordered form. Still, the atoms, they are close to each other, and the solid is formed. This type of solid is known as amorphous solid. Okay. So depending upon the type of component particles and the nature of intermolecular forces, they can be divided into molecular solids, that is, if they have molecular bond, covalent or ionic bond. They might have covalent solids in which the bonds between the atoms is covalent, and there can be a hybrid solid where you have a combination of metallic as well as ionic bonds there. Okay. And these such type of solids are the molecular solids. They are the metallic solids and ionic solids. They combine to form amorphous solids. Okay. So this is the difference between the various phases. Okay. Again, the reverse is also possible. If we heat the solid, it will form liquid. If we heat the liquid, it will form the gaseous form. Okay. Now the solids, as we have already discussed, they can be subdivided into two types. You can have either the crystalline solid or the amorphous solids are there. Now in the crystalline solid, the atoms, ions or moleculars, they are arranged in a definite ordered repeating pattern in three-dimensional form. Examples of crystalline solids can be iron, copper, other metals, and sodium chloride is there. So these are all examples of the crystalline solids. Okay. And as discussed before, amorphous solids, these are randomly oriented atoms, ions or molecules that do not form a defined pattern or lattice structure. The example may be glass. So glass is a amorphous solid. Now, if we look into again the difference between a crystalline versus the amorphous solid. Now, amorphous solid is if the cooling rate is faster than the rate at which molecules can arrange into crystalline state. Okay. So then what happens? Amorphous solids are formed. They are also known as supercooled liquids. Okay. Now, their molecules are arranged in random manner, and the physical properties are they are identical to all in all directions, and hence they are isotropic. They have isotropic properties. Okay. So there are two types of properties are there. There is isotropic property, that is if the properties of any substance is the same in all directions, that is x, y, or z direction, such type of substances are known as isotropic substances. But if the properties they change with direction, say in x direction it has different properties, in y direction it has different properties, in z direction it has different properties, such substances are known as anisotropic, aniso, anisotropic substances. So that's the difference between isotropic and anisotropic substances. Yeah. Now in this diagram here you can see that in a crystalline formation of silicon oxide, also known as quartz, okay, the atoms of silicon and oxide, red is the silicon and blue are the oxides, they are arranged in a definite ordered pattern. Okay, so such type of arrangement where it forms a crystalline solid of silicon oxide, it is known as quartz. Okay, so it's a refined form. Now, if the cooling rate is fast, the same silicon oxide, see the chemical formula is the same, SiO2 in both the cases. The only difference is the ordered and disordered form of elements. So in this case, the silicon oxide forms disordered structure, and this disordered structure is your amorphous structure, and the substance that is formed is glass. Okay, so quartz and glass, they both have the same chemical formula, SiO2. The only difference is the arranged structure in crystalline form, it is called quartz, and disordered structure becomes glass. So this is the difference between crystalline and amorphous solids. Then comes is your what is a monocrystal or a polycrystal is there. Okay. Now on the left hand side you can see the diagram here, diagrams. You have a monocrystalline solid. Okay. So it has the same crystal structure throughout the metal. Okay. In the monocrystal, an atomic structure that repeats periodically across its whole volume. So in the whole volume, you can see here in the three-dimensional diagram, and in the diagram on top here, three-dimensional diagram on the crystal diagram is here. So this is an example of a monocrystal. Okay, the crystal structure, it repeats itself throughout the volume of the metal or the substance. Even at infinite length scales, each atom is related to every other element atom, equivalent atom in the structure by translational symmetry. So this means that throughout the volume, maybe it can the volume may extend to infinity. Even at such an extent, the atom structure, it follows symmetry. So this is an example of a monocrystal solid. Then comes is a polycrystal solid. Now in polycrystal solid, what happens is the structure is followed in a symmetric arrangement up to certain extent, and after that the shape or the crystal, it follow the direction changes. Okay, the orientation changes. So we will find a crystal. If you see, can see the diagrams on top, you will find a crystal formation in a disordered form. Okay, the formation is not orderly form. So at certain extent the crystal forms, after that the direction changes, the crystal changes its formation of crystal changes its direction, and the final crystal formed is a disordered uh, crystal in a three-dimensional space, and such type of crystals are known as polycrystals. Okay. An aggregate of many small single crystals with different orientation with respect to one another. Okay, so in this lattice diagram, you can see that these white lines, they separate the orientation of crystals. In one, these are arranged in horizontal manner. In the other, you can see the phase, you can see that it has tilted. In the third phase, it has again changed its direction. So orientation changes after a certain period of repetitions. Okay, so in each of these regions, the molecules, they are arranged in a separate orientation, and these orientations or minor regions, if you take a single crystal out of that, it is known as the grain of that crystal. Okay, and these white lines that separate one formation of these grains with the other are known as the grain boundaries. So in a polycrystals, we have grains and grain boundaries. Now these grains, the arrangement of these grains is different in different say regions or in different directions. So, and where the grain orientation changes from one another, that region is known as this white line. This is known as the grain boundary of a polycrystal solid. So this is the difference between a monocrystal. In monocrystal, the same grain or the same crystal, it follows ordered pattern throughout the volume, and the volume may extend to infinity. It will follow the same grain orientation and size. But in the case of polycrystals, the grain orientation, it changes after a certain say part. Okay, and we find that the final crystal that is formed, it is not an ordered crystal but a disordered crystal that is extending its itself in different directions. So this is your monocrystal and polycrystal solids. Now, what is the difference between crystalline, polycrystalline, and amorphous solids? Okay. Now, in crystalline solids, you can see here the diagram at the bottom. You have three diagrams here: crystalline solid, polycrystalline solids, and the amorphous solids. Okay. Now, in the crystalline solids, the grain or the order of the element or the crystal, it is perfectly arranged, and this arrangement extends even to the infinite length. So this is if the crystals, they are arranged in an orderly manner throughout the volume and up to infinity, such type of arrangement is known as crystalline arrangement. In polycrystalline, what happens is the grain, they follow the orderly arrangement up to certain distance. After that, the grain orientation changes, okay, and it follows that orientation up to certain distance. After that, again the orientation changes. So there is symmetry of arrangement of atoms up to certain distance. After that, the orientation again changes. So such type of crystals are known as polycrystals. But in the case of the third type, that is amorphous crystals, if you see at the microstructure level, at the atomic level, all the atoms, they are arranged in a disordered manner. So such type of crystals are or solids are known as amorphous solids. So there is no periodic arrangement between the atoms of the solids, even at the microscopic level in amorphous solids. So this is the basic difference between three types of solids, that is crystalline, polycrystalline, and amorphous solids. Next, if we see at this table here, this is table shows the difference between the crystalline and amorphous solids. If you look at the shape for the crystalline solids, it has a definite characteristic geometric shape. Amorphous solids, they have irregular shape. Melting point, it melts at a sharp and characteristic temperature. So, amorphous solids, what happens is it gradually softens over a range of temperature. So इसमें क्या है, the solid turns into liquid abruptly or sharply at the predefined melting point. Okay, but in the case of amorphous solids, because the grain structure is irregular, the melting takes place over a range of temperature, and this it changes into liquid form slowly. Okay, then if we look at the cleavage property, when a crystalline solid is cut with a sharp edge tool, it splits into two pieces, and the newly generated surfaces are plain and smooth. Okay, so this is the property of a crystalline solid. But on the other hand, if amorphous solid, if we cut this amorphous solid with a sharp edge, it splits into two pieces, and the newly generated surfaces are irregular shape. Okay, so उसमें surface is plain and smooth, and in the amorphous solid, the surfaces are irregular. Now, if we talk of the heat of fusion, they have a definite and characteristic heat of fusion. They do not have a definite. Again, the heat of fusion is when the liquid changes into solid changes into liquid. Okay? So that is known as the heat of fusion. So the solid changes into liquid abruptly, okay, or instantly when we reach that say melting point temperature. But in the case of amorphous solid, it takes time. Okay. Anisotropy, if we talk of, this is the crystalline solids, they are anisotropic in nature, and amorphous solids are isotropic in nature. If we talk of the nature, crystallines, they are true solids. Okay, amorphous, they are supercooled solids or pseudo solids. Okay, because the grains, they are not arranged in a regular pattern. Okay, so they are also known as pseudo solids. Order in arrangement of constituent particles. If we see the property, the crystalline solids, they are long range ordered, means this the arrangement of the crystals is repeated through a very long distance, okay, or up to infinity also. Amorphous solids, short range, very short range. So this is the difference between the crystalline and the amorphous solids. Now, if we look into the next slide, that is what is a crystal? A crystal or a crystalline solid is a solid material whose constituents such as atoms, molecules, and ions are arranged in a highly ordered microscopic structure, forming a crystal lattice that extends in all directions. So if we define a crystal, this means that the arrangement of atoms, molecules, and ions in a crystalline solid, it is highly ordered, like you can see this diagram on the right hand side. Okay, so all the atoms and the molecules of the different elements, the green is say some other different element, purple is the different element, so it's a combination of two elements, and the structure formed is in a orderly manner. So there is no disorder you can see here. Okay. So, and this order structure, it extends in all directions. So such formation is known as a crystalline solid. For example, gold, silver, diamond, sodium chloride, sugar, iodine, uh, all these are examples of crystalline solids. Now, if we define what is crystallography, crystallography is say it's a fancy name given to the study of crystals. So study of crystals, basically it is just the study of crystals. It is called crystallography. So what is done in crystallography is we study the crystals and the formation of crystals. In crystallography, the process of crystal formation via the mechanism of crystal growth is called crystallization or solidification. So what we do in crystallization, this diagram shows here, what we do, we take a crystal, we pass the X-ray through it, okay, and through the diffraction pattern or X-ray diffraction pattern, we look into the microscopic view of the crystal, and then we look into the atomic model of the crystals formed. Okay. And then we study the various crystal formations that are there in the crystalline solids. Okay, in crystallography, what we do is we study the crystals. Okay, so one of the examples is given here where the X-ray diffraction of the crystal solid is shown here. Okay. Now, when we go on to the atomic model, in atomic model, what we observe here is say the grains, they are disordered in shape. So what we can do is we can go back and we can go for the refinement of the formation of crystal if we are developing that crystal artificially. Okay. So we can, after studying through the X-ray diffraction, we can go back and see where we can modify that crystal or refine that crystal so that a monocrystal or the required orientation of atoms can be achieved. So that is crystallography. Now, why we need to study crystallography? Now, material properties are intimately related to their structures. Okay. So this means whatever we want to build, if we want to build any structure or any automobile or any device that we are going to use, we need to predefine the properties that are required here. So if I want to make a car, so the body of the car now should be such that it should absorb the shock of impact, so that that impact does not reach the passengers, and passengers are can be saved from the injury. So I have to go for a material that has such properties. So this means that the material properties, they are very much important, and we should know the properties of the materials. And this can be done with the help of crystallography. Okay. Now, understanding certain properties require knowledge of the atomic arrangement. For example, in piezoelectric. Now, in piezoelectric is what? Where if we compress any crystal, that compression gets converted into electricity. Okay, so that is piezoelectric. So we need to know or understand the atomic arrangement or the structure of the crystals in such case. So crystallography is again important in piezoelectrics. In enzymes, we can study the active sites of enzymes, okay, and we can inhibit the inhibitors where those enzymes are actually growing. Okay, so here if you see the say example we take is uric acid. Okay, now in body, if uric acid is formed at a higher rate, what happens, it gets and if it is not flushed out through the, or it is not say flushed out through the kidneys. Okay. So what happens that that uric acid, it forms crystals, and the crystal growth takes place within the joints. Okay. So by studying the growth of crystals, we can go for inhibitors. Okay, so we can take that particular medicine, and we can get rid of those crystals. Okay. So this is very important, the study of crystallography. Now, impact of crystallography can be seen because there are a lot of Nobel prizes. Many scientists, they are getting Nobel prizes in the field of crystallography and diffraction. Okay. So this study of crystallography is important. Now, if we go into the historical development of crystallography, now this person, that is Wilhelm Cornard Röntgen, in 1895, he discovered X-ray. Okay, so what he did was he accidentally discovered X-ray when he passed the rays through a crystal structure. Okay, so interested in the effects of ultraviolet radiation, he covered a cathode ray discharge tube with black paper and darkened the room. With the glow from the tube hidden, Röntgen was surprised to see the fluorescent screen 2 meters away. Okay. So he discovered X-ray. Then in 1912, Max von Leu discovered that X-rays are diffracted by crystals. Okay. So he used copper sulfate, and he examined that the copper sulfate crystals, what they do is they diffract X-rays. Diffraction means one is a reflection and the other is diffraction. They let the light pass through the crystals, and it can come out through the other side, and it gets diffracted into different directions or different orientations or at different angles. Okay. In 1930, Sir William Henry and William Lawrence Bragg formulated their Bragg's law. So that was when the birth of crystallography took place in 1913. The first crystal structure ever solved was sodium chloride, that is your table salt. It clearly showed equally spaced sodium and chlorine atoms, and thus provided the concept of ions and ionic bonding. Okay, so the first crystal structure that was solved was sodium chloride by Lawrence Bragg and William Henry. Now, in today's world, or today in this time, what is possible today? Okay. So you can determine the small molecular structure in routine nowadays. It was not possible 50 years ago. The structure can be determined within 6 to 12 hours. Okay. So the crystal structure determination is very fast. Nowadays, crystal structures of macromolecules can be solved for single crystal data. The synchrotron radiation can, in some cases, yield a single crystal structure from crystals as small as 10 micrometer. Okay. So, and even from the powder, crystal powder, it is now possible to determine the crystal structure of that crystal. Okay. So this is what is possible today in crystallography. Now, before we move further, there are certain definitions we need to study. The first definition is what is a crystalline material? It is a material that is comprised of many or one or many crystals. In each crystal, atoms and ion show a long range periodic arrangement in ordered form. So these are crystalline solids. Then what is a single crystal? A crystalline material made up of only one crystal. Okay. There are no grain boundaries. So this is known as a single crystal, or it is also called monocrystal. Okay. If you look into the unit cell, of the crystal, that unit cell, it repeats itself throughout the volume of the crystal. So hence it is known as single crystal or monocrystals there. Now, in polycrystalline material, grains are the crystals in a polycrystalline material. So here you can see this is the structure of a polycrystal. So you can see that the grains or the orientation of the regions is different in different directions. And you can see these grains, the orientation of the grains in this region, the orientation is like this. In this second region that is next to this previous region, region A, region B, you can see the orientation has changed its direction. Okay. In the next region, the orientation is different. So in polycrystalline metal, the orientation of the crystals or the grains is ordered but in different orientation to one another. Okay. So if you see this grain A, B, and C, the orientation that is unit cell, the orientation is in different directions, and these regions are separated by these grain boundaries. The region that separates one grain from the other is known as the grain boundary is there. Okay. So polycrystalline material is a material that is comprised of many crystals as opposed to a single crystal material in a monocrystal. Okay. And the grain boundaries are region between grains of a polycrystalline material. So that is the difference between monocrystals and the grains and polycrystal materials and the grain boundaries. Now, if we talk of the crystal structure, a crystal structure is a regular and repetitive three-dimensional pattern in which atoms of a crystalline material, they arrange themselves. So that becomes your crystal structure. If we look at if we go for a single unit cell, and that unit cell, it repeats itself throughout the volume, it becomes your crystal structure. This can be defined as a regular repetition of three-dimensional patterns of atoms in space. To some extent, the repeating pattern controls the external shape of the crystal. Now, a crystal structure is characterized by its unit cell, a small imaginary box containing one or more atoms in a specific spatial arrangement. So a unit cell is, it is an imaginary, small imaginary three-dimensional box that contains the specific arrangement of atoms in it. Okay. So the unit cells are stacked in three-dimensional space to form the crystal. So these unit cells, they are stacked one on top of the other, and this unit cell, it repeats itself throughout the volume of the crystal. Now here you can see the space lattice. Next is space lattice. It is an infinite periodic array of mathematical points in which each point is identical surrounding to all others. Okay. So this means if we have these points here, these points are arranged at equidistance from each other and equally angled from each other. Okay. In is हर एक point क्या है? It is at same angle to the nearest atom. So if we take this atom, it is arranged in orderly manner in x direction and orderly manner in the y direction also. Okay. Now if I place the atoms at these points, say this is our this fish is an example of our motif or the basis. So this fish can be placed at the points. Okay. And we will see that this arrangement is repeated. So this becomes your unit cell, and this unit cell is being repeated one after the other, and this forms the crystal structure. Okay. Or this fish can be placed in between these four points or atoms, and these four atoms, they form the unit cell. So this unit cell is repeating again and again and again in all directions. So this forms your crystal structure, and these points are known as the lattice points of the structure, crystal structure. These points are the lattice points of the crystal structure, and these lattice points, they are arranged in ordered definite direction and spacing from each other. Okay. A crystal structure is a periodic arrangement of atoms in a crystal that can be described by the lattice. Okay, these are the lattice points. So here you can see the lattice points are a purely mathematical concept, whereas atoms are physical objects. So you need not mix atoms and lattice points with each other. The lattice points do not necessarily lie at the center of the atom. Now, in the previous example, if you see this fish is an atom. So the arrangement of this atom can be anywhere. It can be at the lattice point, or it can be in between the lattice points. Okay. So hence, the lattice points do not necessarily lie at the center of the atom. Okay. So here you can see that this is an example of a crystalline material in which these circular spherical balls are the atoms. Now these atoms are arranged in a definite order in all the x, y, and z direction to form a crystalline solid. Now these atoms can be replaced by small dots to form this lattice diagram. So these points might represent these atoms that are placed at say definite order. So this diagram can be simplified into lattice structure. This is my lattice structure, in which the end points, they are or the corner points are depicted by small dots or lattice points, or lattice is there. So this is my lattice structure. This is my atomic structure on the left hand side, and this is my lattice structure. Okay. So if I talk of a unit cell, it is the basic structural unit of a crystal structure. Its geometry and atomic position define the crystal structure. It is the smallest part of the unit cell, which when repeated in all three directions reproduce the lattice. So in this bottom diagram, you can see on the left hand side, this is my crystal lattice. If I take the basic single unit cell out of it, this shaded portion, this is my unit cell. Now this unit cell, if I place unit cell on top of the unit cell on the right hand side, everywhere, if I repeat this in all three directions, that is x, y, and z direction, I will form the crystal lattice. So this means this unit cell on the right hand side, this is my unit cell. So this is my smallest basic part of the crystal lattice. If repeated in all directions, it forms the crystal structure. Okay. So if I talk of the terminology, we follow the right hand rule in this case. So we start from so it will have x direction, the y direction, and the z direction. Okay, the distance of say if this point is the center point of the atom, so distance between one atom from the other atom in x direction is given as by a. The distance of atom from the other atom in z direction is c. The distance from this atom from the other atom in y direction is b. Similarly, the angle between x and z is known as beta. Between z and y is alpha, and x and y direction is gamma. So these are the basic lattice parameters by which we can define the unit cell. Here it is again in clear, we have this unit cell here. So different lattice parameters are the axial length. In x direction, the length of the unit cell is given by a. In y direction, it is given by b, and in z direction it is given by c. Then interaxial angles, you can say interaxial angles means the angle between y and z is alpha, then your z and x is beta, and x and y is gamma. There. And similarly, the unit vectors, in x direction it will be a vector, in y direction will be b vector, in z direction will be c vector. Now, all unit cells may be described via these vectors and angles. Okay. So this is the basic terminology or the lattice parameters. ABC are the lengths of the unit cell in x, y, and z direction, and alpha, beta, and gamma are the angles, interaxial angles between x, y, yz, and z, y direction or axis. So this is the terminology that is universally used for defining the various parameters or the lattice parameters of a unit cell. Now, these unit cells, they basically come in 7 different classes. Okay? And each of these 7 different classes are different depending upon the unit cell parameters. So these unit cells can be of 7 different types. The first one is your simple cubic. In simple cubic, the angle or the side A is equal to B equals to C, means all 3 sides are equal and all 3 angles are equal to 90 degree. Alpha is equal to beta equals to gamma equals to 90 degree. So this is your simple cubic unit cell. Next type is your tetragonal. Is there in tetragonal, the side of the base, that is your A, equals to B, but C is not. C here is long, so C is not equal to A and B. A equals to B, but it is not equal to C. But angles alpha equals to beta equals to gamma, all 3 angles are equal to 90 degrees there. Next is your orthorhombic, or it is also known as cuboid shape. In this, what happens is all 3 sides are non-equal. That is, A is not equal to B, is not equal to C, but angles alpha equals to beta equals to gamma equals to 90 degree. So this is your orthorhombic. Then comes is your rhombohedral. In rhombohedral, the sides are equal. That is, A equals to B equals to C, but the angles, that is your alpha equals to beta equals to gamma, all 3 angles, they are different from 90 degree. So all angles alpha, beta, and gamma, they are different. Okay, so here alpha is less than 90 degree. Okay, beta is greater than 90 degree, and your gamma is again greater than 90 degree. So such type of shape is known as rhombohedral shape. Then is your monoclinic shape. In monoclinic shape, all 3 sides are different. A is not equal to B, is not equal to C, but the angles alpha equals to gamma equals to 90 degree. So this angle alpha and gamma is 90 degree, but beta, this angle beta is not equal to 90 degree. This is your monoclinic shape. Then comes is your triclinic shape. In triclinic shape, all the sides are different in length from each other. That is, A is not equal to B, not equal to C, and all the angles, that is your A is not equal to alpha, is not equal to beta, not equal to gamma, and they are all not equal to 90 degree. So all the angles are different from 90 degree. So such type of shape is known as triclinic shape. And then comes is your hexagonal shape. In hexagonal shape, the A, if I see here the hexagonal shape, the unit cell, if we take this cell which is on the top face and the bottom face, so this becomes the unit cell. So this becomes the unit cell that repeats itself. So in this case, A is equal to B, but it is not equal to C. C is different. Okay. A is equal to B, A is equal to B, but it is not equal to C. Okay, and alpha is 90 degree, beta is 90 degree, but gamma equals to 120 degree. This gamma angle, so यहाँ पे this alpha angle is 90 degree, beta angle is 90 degree, but this gamma angle, it is equal to 120 degree. So depending upon the unit cell parameters or lattice parameters, that is A, B, and C, alpha, beta, and gamma, we can have 7 different types of unit cells. Okay, and they are simple cubic, tetragonal, orthorhombic, rhombohedral, monoclinic, triclinic, and hexagonal shape.